Hello everybody, it turns out that there is a way to represent the voltages and the currents across a transistor graphically. So let's just draw a transistor and then we see how to represent the various voltages and currents graphically. So we had C as before, E, and here we had B, and that's just a model for the transistor, and how to represent the various currents and voltages graphically. So we can have a coordinate system, and the x-axis is BE, the y-axis is IB. And here we have approximately 0.5 volts, and the graph between VBE and IB is going to look roughly like this. And this is roughly 0.7 volts. So as we can see, when VBE is less than 0.5 volts, IB is 0. And that's indeed, we saw previously that is the cutoff region. This is the cutoff region. And when it's above 0.5, that will be either the active region or the saturation region. Whether it's active or saturation depends on VCE. And then we have another curve for the relationship between VCE and IC. That curve is a little complicated. I'm a little worried about getting it right, so I'll draw it pretty big. So that will be IC. And here we have VCE. And the key is to remember the relationship that IC is equal to beta IB, and beta is usually 100 IB in the active region. So let's pick a few possible values of IB. In fact, let's just pick one. Let's for now start with picking one. Okay. This is supposed to be a straight line. Okay, so let's say it's straight line from in onwards. And it's going to be straight line all the way to more or less forever. Okay, so this is 0.2 volts. And what is this green graph? The green graph is the particular value that IB takes. For example, IB, let's say just so happens that VBE is just so happens to equal to 0.6. Let's just so happens, okay, it's 0.6. So let's say what value IB will take. So the value that IB will take will be, okay, I'm just going to draw a string. Right, so when VBE is 0.6, I'll draw it a little bit. Okay, it's going to be messy, so let's just try to draw it correct the first time instead of fixing it later. I guess that's as good as I can do. And then, okay, and then this value is just 0.6. So when VB is 0.6, IB is going to be equal to something. Depends on the pink curve here. So let's say this value, I'm just making it up, it's just going to be 1. Just for ease, let's say just 1 ampere. So let's say this is imaginary, but just to make it simple, VBE is 0.6 volts and IB is 1 ampere. Just so happens to be 1 ampere. Of course, this is based on this pink curve. This is the intersection of the pink curve with the y-axis is the value IB is taking. Very well. And let's say this green graph represents IB equals to 1 ampere. This green graph came to us from looking at the VBE IB. We know that VBE is 0.6, IB is the value of 1 ampere. And then we put IB, the whole green graph is IB equals to 1 ampere. This whole green graph is what happens to VCE and IC, what is the relationship between VCE and IC when IB is equal to 1. And there are two things to see. When VCE is bigger than 0.2, when it's bigger than 0.2, then IC is just going to be 100 IB. So in that example, IC is going to be 100. So when VCE is, for example, 0.3 or something like that, well, VCE is 1.3, IC is going to be 100. When VCE, let's just say this is 7 volts for all we know, not to scale. Okay, what is 7 volts? What is going to be IC? It's still going to be, if this is supposed to be a straight line, it's still going to be 100. So as long as VCE is bigger than 0.2, we're in the active region. And in the active region, IC is 100 times IB. But here, this area is the saturation region. This is the saturation region where VCE is smaller than 0.2. In that case, VCE, or in that case, IC is going to be less than 100 times IB. In the saturation region, indeed, IC is less than 100 times IB. So let's say that we have VCE at 0.1 volts. VCE at 0.1 volts, let's say it's here. And what is the intersection with IC? The intersection IC, for example, let's imagine it is 70. So you can see that it's a straight line. When IB is equal to 1, if VCE is bigger than 0.2, no matter how much you increase VCE, if VCE is already bigger than 0.2, IC is just going to be 100 IB. But if VCE is less than 0.2, and that's a saturation region, then IC is going to be various values that are less than 100 times IB. Various values that are less than 100 times IB. So for example, here, oh, let's, so for example here, let's say this is 0.2, and it's supposed to roughly like this, and then after this it's a straight line. So this is VCE. And we can see that, hopefully it can be seen that when VCE is less than 0.2, for example, VCE could be 0.1, and if this value of IC is 100, and this value of IB is 1, we can see that below 0.2, the intersection of VCE and IC could be something like 70. And of course, when you decrease VCE, it's going to be lower and lower. Okay. And this is the case for one graph. This is the case for one particular value of IB. In this case, IB is equal to 1. We have two more cases to consider, unfortunately. So just try to, two more cases to consider. Fortunately, okay, something like that, and then, okay. And in two more cases to consider, in this case, just need to change it. Let's draw the whole thing again. Now it's two, sorry, just, I need to change it to a pen. Okay, good, now it's okay. Two more cases to consider. Bad luck, okay. No. Why? Okay, I think now it's okay. Two more cases to consider. This is what the case is if IB is equal to 0. Well, if IB is equal to 0, that's a simple case. This is IB equals to 0, then no matter what VCE is, IC is also going to be equal to 0. So this is the cutoff condition. So this is the cutoff. This curve represents the cutoff condition. IB 0, IC 0. This is one case. And the only other thing is that we saw this graph. So let's assume this is 0.2 here. And we saw this graph for a particular value of IB, and many graphs for many different values of IB, many graphs of many different values of IB can be drawn in the same axis. This could be IB equal to 2. This is going to be IB equals to 3. And right, so IB equals to 3. And so and of course, at a particular moment, at a particular configuration, IB takes only one of those. It cannot take but 1, 2, or 3. It can either be either 1 or 2 or 3 or some other value. So IB is only equal to one value at a time. It's not going to be equal to all 3 values. It's only equal to one value at a time. Very well, it's only equal to one value at a time. But just to say, what if it were equal to 2? Or if it were equal to 2, we would have this graph. What if it were equal to 3? If it were equal to 3, we would have this graph. And so just to say, to show what would the relationship between VCE and IC look like, or rather, not exactly that, but what would be if, yes, for a particular value of VCE, for what would be the value of IC given a particular value of IB? So what would this relationship between those 3 things be like? Well, the relationship, we can draw several graphs of IB at once and see the relationship. In all cases, though, and this is the most important point, in all cases, this value is going to be 100 times IB. This is going to be 200. This is a little bit too big, but too tall, but it's going to be 300. So that when the voltage is, let's say the voltage here is 3, when the voltage is VCE is above 0.2, IC is 100 times IB. Any number above 0.2, IC is 100 times IB. On the other hand, when the voltage is 0.2 or less, or let's say less than 0.2, the corresponding value of IC is going to be less than 100 times IB. Maybe it's 70 here. Maybe for this graph, it's 150. Maybe here it's I don't know, maybe here it's 250. So if we have a value of 0.1, 0.1 is less than 0.2, then the corresponding value will be, for particular value of IB, the corresponding value of IC is going to be less than 100 times IB. And again, I draw 3 graphs for 3 different values of IB in the same time, but in reality, as we saw, IB can only take one value at a time. The drawing of the 3 graphs is something like to say, well, what if IB was 1, then we see this. If IB was 2, we see this. If IB was 3, we see this. But at a given time, IB cannot be both 1, 2, and 3. IB is either 1, or it's 2, or it's 3, or it's some other value. It's just this way we can graphically see what the value of VCE and IC and IB, what the relationship would be like if IB were to take this value, and then what the relationship would be like if IB were to take another value, what the relationship would be like if IB were to take a third value, and so on. Alright, so hopefully it kind of made sense. Try to explain it. I'm not the best at explaining things, but as may be. Okay, great. So thank you for watching this video, and thank you.